In this video, we're going to look at some practice problems relating to the antiderivative graphically and numerically, thinking about the fundamental theorem of calculus and the relationship between the antiderivative and the original function. So first, let's think about just algebraically finding antiderivatives of functions. Again, this is going to be a topic more for section 6.2, but it's good to get some practice before then. So first, we need to find a function whose derivative is x to the 17th power. And when we think about derivative rules, our mind might go to the function x to the 18th. We know that the derivative of x to the 18th is 18 times x to the 17th, and there is something important there, that x to the 17th, but we're off by a factor of 18. So to get rid of that, we can divide by the 18 and do 1 over 18 x to the 18th, and that is an antiderivative of x to the 17th. And in fact, 1 over 18 x to the 18th plus c for any constant c is an antiderivative here. What about for the function 5? Well, we get a derivative of a constant when we take the derivative of a line. So if I have something like 5x, the derivative there is 5. And in general, this means that 5x plus c for any constant c is an antiderivative here. And you can double check that by just taking derivatives of those functions and verifying that you get 5 out. And the last one here, e to the 2x, is a little bit more complicated. When we think about what has a derivative of e to the 2x. And if you're thinking about it on your own, we know it has to be something with e to the x, but e to the x itself doesn't work. It would have to be something like e to the 2x. But that derivative is 2 e to the 2x because we have to use the chain rule and multiply by the derivative of the inside. So to get rid of that, we need to have 1/2 e to the 2x to get rid of that extra 2 out in front. And in general, 1/2 e to the 2x plus c for any constant c is an antiderivative. This is, again, looking forward to the next section a little bit, but it's good to get some practice before we get to that point. All right. Now thinking about graphs of derivatives and how we get information about the function. So here we have the graph of f prime, and we're also given some areas under the curve. So for instance, this area here is equal to 1. This area here is equal to 7. And this area here is equal to 2. And we're thinking about our function itself. Sorry, the derivative, and thinking about information about the function itself. So, given that information and the fact that f of 0 equals 5, remember that's something that tells us where the function is going to start, we are going to find ordered pairs for the local extrema points. So we know that the local extrema points are going to occur at critical points. That's going to be when the derivative is 0 or does not exist. And in this particular example, it's just going to be when the derivative is 0. So that's going to be at 1 and 5. And we could classify these critical points, something we did in the previous video. we could say that x equals 1 is going to be a minimum, x equals 5 is going to be a maximum using either the first or second derivative test. Something we also did is that around x equals 3, it's not quite at x equals 3, but we'll say around x equals 3, we have an inflection point. That's when the derivative of the derivative, that's the second derivative, is equal to 0. We have a horizontal tangent line at that point. The derivative changes from increasing to decreasing at that point. That means the concavity is changing from concave up to concave down. All right, so we have these 3 points that we're going to be looking at, 1, 3, and 5, and I want to find the ordered pairs. That means I need to find the function values of those points. So I need to find f of 1, f of 3, and f of 5. And I'm going to use the fundamental theorem of calculus to do that. I know that the integral from 0 to 1 of f prime is going to be equal to the f of 1 minus f of 0. And this area is equal to negative 1 as we're below the x-axis. F of 1 and f of 0 is 5. So this means that f of 1 is going to be 4. To find f of 3, we could do the integral from 0, or how about from 1 to 3 is going to be f of 3 minus f of 1. And this area is going to be half of that parabola. It's going to be about that, I should say. That area is going to be 7 halves. It's like we're taking half of that area. That's going to be half of that 7. So 7 halves is going to be f of 3 minus f of 1, which you just found was 4. That means that f of 3 is going to be about 15 halves. And finally, let's find f of 5. We can do the integral from 3 to 5. F prime is going to be f of 5. Let's do actually 1 to 5. Don't have to deal with any fractions then. F of 5 minus f of 1. That area is just 7. F of 5 is what we're looking for. F of 1 is 4. That means f of 5 is going to be 11. And there are our ordered pairs for our critical points, or for our extrema points. We have a min or max at 1 and 5, and we have those 2 points. And then 3, we have an inflection point at about 15 halves, 7.5. So on the next page, we have a table of values. We're also including the value for f of 6. We could have found this with the fundamental theorem of calculus as well, doing the integral from 5 to 6 of f prime, f of 6 minus f of 5, to find that 9. But if we have that information, can we sketch the graph? Well, first let's plot those points in the function. We have f of 0 equals 5, f of 1 is 4, f of 3 is about 7.5, f of 5 is 11, and f of 6 is about 9. And we found that we have at 1, 4, we have a local min. At 3, 7.5, we have an inflection point. And at 5, 11, we have a local max. So we could have seen that on the previous page as well. just based on the first and second derivative test for those points 1 and 5. We know that the derivative goes from negative to positive. That means we have a min there. At 5, we go from positive to negative. That means we have a max. Or we can think about the second derivative in those cases. So putting that all together, we have a nice curvy function. We have a min at 1. We have an inflection point at 3 and a max at 5. Our function is going to look something like that. And again, the point is that we are finding information about the original function given the derivative. Let's do one more problem here. Estimate the function values for 3, 6, and 9, given these table of values for the derivatives. This time we don't have a picture, but we have a table of values to find these. And we're going to use the fundamental theorem of calculus again. So we know that the integral from 0 to 3 of the derivative is going to be equal to f of 3 minus f of 0. The difference in this problem is that we don't know the exact value, but we can estimate this area using a rectangle. So we have f of 0, f of 3, sorry, f prime. We here have 2018. And we can maybe use the value at 18 and do a rectangle. It's like a right Riemann sum kind of thing. And we say this is going to be about equal to, we do a left Riemann sum as well with the 20. Doesn't really matter. We use a 20 because it's easier. We can say this is equal to 20 times 3. Equivalently, you could do or 18 times 3. Either one's really fine. Let's do 20 times 3 because it's going to be a little bit easier to calculate. This means that we're going to have 60 is equal to f of 3 minus f of 0, which is 10, given in the problem. This means that f of 3 is 70, about. This is approximate. Let's do it again for 5. This time let's do the integral from 3 to, sorry, not 5, 6, f prime. And we'll do a similar thing here. We're going to estimate the value at 6 using the values of the derivative. Here, that's 14. And we could use a right or a left Riemann sum. Since we did the left one before, let's do the left one again. We'll say this is equal to 18 times 3, height times the base. We're looking for f of 6. And we know f of 3 is about 70. So 18 times 3 is going to be 54. Plus 70 is going to be about f of 6. So f of 6 is about 124. And one last one. We'll do the same thing for 9. F of 9 minus f of 6. Once again, look at 9. The function value is 13. We could use a left or a right Riemann sum. Doesn't really matter. We'll use the left one since we did that before on all of them. That means that we're going to have 14 times 3 for the area there, equal to f of 9 minus f of 6, which is about 124. 14 times 3 is going to be, 14 times 3 is 42. F of 9 minus 124, that means that f of 9 is going to be about 166. So in this example, we're doing similar things we've done before. We use the fundamental theorem of calculus all over the place. Now we're estimating the areas with rectangles, either using a left or right Riemann sum kind of idea. And it's really pretty similar past that. In the next video, the last two sections of this course, we're going to be looking at antiderivatives as we did in the first example in this video, and looking at indefinite integrals, and then looking at the second fundamental theorem of calculus.